Well, let's dive into 13.7 together. We're going to talk about surface integrals. And just like we did line integrals of different functions over a curve, we did line integrals of both scalar functions and vector fields over a curve C. So we can do surface integrals over a surface of both scalar functions and vector functions. And there's a really remarkable similarities with the formulas. And so I'm going to try several times to point out just the similarities in the way things are defined. So with that in mind, let's go ahead and look back at line integrals of scalar functions. So we learned back in the beginning, 13.2, if you integrate the function 1 with respect to arc length, then you get out the arc length of C. And so we interpreted this as just the integral from a to b of the length of r prime. And then if you want to integrate a general scalar function f, you just have f plug in r times, again, the length of r prime. And so you're going to see a very similar formula here. I want to point out to you when we talked about line integrals of scalar functions that there were no tricks. When you're integrating a scalar function, you always plug in and multiply by length of r prime. However, when you're working with line integrals of vector functions, it's a similar formula. We'll see the formula later, but there are tricks. It's the line integrals of vector fields where the tricks come into play. And so, for example, what kind of tricks am I talking about? Well, the fundamental theorem of line integrals, and we also had Green's theorem. I can't write today very well. Let me slide this iPad forward. We also had Green's theorem. So keep that in your mind. When you're doing line integrals of scalar functions, there's no rich theory, but when you're doing line integrals of vector fields, then I really should say vector fields here technically, then interesting things can happen. So same is going to be true for surface integrals. All right, so one more review. In the last lecture, we talked about the surface area of parametric surfaces. And so we said, look, if you integrate the length of this r partial u cross r partial v, then you actually get the area of S. And look at the similarity here. Okay, integral length, and that should be a r hat there. Scroll up, and integral length of r prime, you get the length of the curve. Here we're integrating the length of this normal vector, and we get the area of S. Okay, so what is a surface integral of a scalar function? Well, here we go. So we're going to take a surface S parametrized by r of u and v over some region D. And then I want to pick my scalar function f, and I do want to require that f is continuous on S. It's got to be reasonably well behaved. So then the surface integral of little f over S is defined as follows. Here's how we write it, and here's how you interpret it. So we write double integral, and then we say sub S. S is telling you this is a surface integral. Then you write down your function f, and then you say ds. And so this is, what do? Exactly what you did for line integrals. Look back up here. Line integrals of scalar functions, you plug in the parameterization, you multiply by the length of a certain derivative. Okay, same thing here. You're going to plug in your parameterization, so we're going to switch now to integrating over our region D, and then I look at f of r of u and v. I plug in the parameterization, and I multiply by that same length of, that's a u, r partial u cross r partial v dA. So really similar relationship. So I went ahead and put that in the notes, actually. So notice the similar relationship to line integrals of scalar functions. F of the parameterization times the length of a certain derivative, f of the parameterization times the length of a certain derivative. And then again, we said this already, but when you pick 1 for your function, then you just get out the integral of the length of ru cross rv, which we know from last time is just the surface area of S. So lots of similarities here. Let's break this video here, and in the next video we'll dive in and do an example.